Hello, my name is Yashoteja Prabhu. I am a researcher at Microsoft Research India. This talk will introduce to you a new machine learning paradigm called as Generalized Zero-Shot Extreme Classification, which has the potential for many real-world applications. This paper has been published in KDD 21. The structure of the talk is as follows. We will begin by setting up the context for the rest of the talk. After this, we'll understand some of the core technical contributions of our work. Thirdly, we will look at some experimental results which validate our technical contributions. Finally, we'll conclude with a brief summary. In the digital world, there are many applications where the user expects a small set of relevant items to be retrieved from a large pool of available items. Examples include information retrieval, where web pages need to be retrieved for a given query, object recognition, where objects need to be identified in a given image, and recommendation, where products need to be recommended based on a user's browsing history. Such applications are often characterized by millions or even billions of items in the pool. As a result, automated solutions are a necessity for handling such problems. In addition, these solutions should also be able to handle an evolving item pool where new items get continuously added. Extreme classification is a branch of machine learning which aims to provide highly accurate and scalable solutions to such large-scale problems. A dominant idea in extreme classification has been to simplify this problem into multiple subproblems by assuming that each item is independent of other items. This would then allow us to learn a separate personalized classifier for each of the item. By pooling the individual judgments of millions of such item classifiers, highly accurate predictions can be made. Such approaches have had many success stories in recent years. Unfortunately, such approaches also have a major disadvantage that they cannot handle new items. Since new items do not carry any historical user feedback with them, individual classifiers cannot be learned for them. In addition, since these approaches also assume that item classifiers are independent of each other, no information can be shared from the old items to the new items. As a result, these new items, which often contain fresh and niche information, can never be recommended to end users. To address this limitation, new kinds of approaches are required which can accurately predict relevant items from millions of both old and new items. We refer to this paradigm as generalized zero-shot extreme classification problems, since we are generalizing extreme classification from old to also predict new zero-shot items with no training data. In formal terms, this involves learning a function f which maps a user input x to a subset of items where item set is referred to as y, which is a union of both old and new items. The main contribution of our work is the development of a new algorithmic technique known as ZestXML for generalized zero-shot extreme classification tasks. ZestXML eschews the idea of independent item classifiers and instead learns a common shared classifier for all the items. This is a text-based model where both user inputs and items are represented through the textual descriptions. Then an item is deemed relevant to a user input if their textual descriptions are similar to each other. Mathematically, we represent this through a bilinear function between the bag of words feature vectors of the user input and item. These feature vectors are sparse high dimensional vectors where the dimension is equal to the vocabulary of the given language. Note that since both the bilinear parameters as well as the vocabulary for representing items are shared between all the items, information can easily flow from old to new items. To use ZestXML, first we have to train the bilinear function f to assign high scores to relevant user input comma item pairs and low scores to irrelevant pairs. We leverage historical user feedback data for training this function. Such feedbacks are available in vast quantities in the form of user clicks in many large-scale search and recommendation applications. The training objective would then iterate through every pair of user input comma item and try to classify it as either relevant or irrelevant. This results in a binary classification problem with a convex objective. However, despite its simple appearance, this problem is intractably hard to solve using simple means. Since there are millions of user inputs and items in the training data, the total number of terms in this objective function would range in 10 to the power of 12. At the same time, since the vocabularies on both user input and the item side can range in millions, the total number of parameters of this model can be in 10 to the power of 12, which would require terabytes of RAM just for storing the model, let alone optimize it. As a result, no conventional first order and second order optimization techniques are applicable here. To meet these stiff challenges, we propose our own specialized optimization technique, which involves two separate stages. In the first stage, we make some key approximations about the objective to simplify the objective considerably, which results in a reasonable solution very quickly. Firstly, we assume that the objective takes a quadratic form. This allows a simple single-step optimization based on the Hessian of the objective. Secondly, we assume that each feature is generated independently of the other features. This further simplifies the computation of the Hessian inverse and results in a closed form solution for the final parameters. Note that these final parameters can be computed by iterating only over the relevant pairs of user input comma item, and we don't have to go through irrelevant pairs at all. As a result, this computation is very quick and can complete in just a few minutes of CPU time. Since these approximations do not strictly hold in practice, the derived solution might be suboptimal. Nevertheless, the approximate solution is fairly accurate at identifying the most informative feature pairs in the parameter matrix W. We use this information to sparsify the parameter matrix W in a significant manner, thus bringing the model size to just a few GBs. Then we have an additional optimization step for refining the values of the retained parameters. This optimization involves solving the original binary classification problem, but instead of using all the user input comma item pairs, we only take the most erroneous pairs in the approximate solution. As a result of these two kinds of sparsifications, the refinement step is fairly efficient and can be done in just a few hours of CPU compute. Once the ZestXML model is trained, it can be used to predict the most relevant items for a test user input. The items with the largest X transpose W Z scores are deemed to be the most relevant for the test user input. This operation is conducted by first projecting the user input X into the space of items Z by multiplying with the parameter matrix W. Then the search can be conducted by using a clever inverted index based data structure, which ensures high scalability to large number of items while also allowing quick indexing of new items. There are some theoretical results which show that under some mild assumptions, the prediction algorithm can be extremely efficient in ZestXML. We validate the effectiveness of ZestXML by conducting various experiments across multiple datasets belonging to multiple real-world applications. To simulate the real-world settings, Our training and test sets are created so as to belong to two successive non-overlapping time periods. It is observed that our created datasets are naturally imbued with a large number of new labels. For example, our largest ads dataset has 30 million labels, and 30% of these labels are new labels which are only seen at test time. We measure the prediction accuracy by the fraction of the top predicted items that are relevant for a given test input. The larger this fraction is, the more accurate are the item predictions for the test input. As we can see, ZestXML is significantly better than many state-of-the-art non-zero-shot extreme classifiers like Attention XML, Dismic, Parable, etc. This is because ZestXML can leverage all the new items also to make accurate predictions for the user input. It's also observed that ZestXML can outperform ANNS on popular dense embeddings such as fasttext and BERT-based embeddings. ZestXML is also found to be highly efficient and scalable. In fact, it only takes a few hours on most of our large datasets to train. It only takes a few milliseconds to predict for a given test input, and its model size is just a few GBs. All these useful properties enable ZestXML to be extremely useful in real-world deployments. Another exciting property of ZestXML is that its predictions can be interpreted by looking at the feature pairs which triggered such a prediction. A book prediction can be interpreted as because of its topic, or because of its author, or because it belongs to a particular book series. Such interpretations often reinforce the trust in our predictions by the end users. To summarize, this talk introduced a new paradigm known as generalized zero-shot extreme classification, which has potential for many real-world applications. This talk also developed a new, highly accurate, scalable, and interpretable algorithm called as ZestXML for such applications. The code for ZestXML is publicly available for research purposes at the below link. Thank you.